point. Generally speaking, I'm probably more likely to give somebody a point today, unless they're off the mark
everybody a
and they're
point.
incomplete. But if you noted that I was saying more than you were, fill that in, because everything I was saying on that sugar code is things I'm going to be assigning points to, right? You don't want to miss it off. Like, I didn't talk about alpha beta. Oops. Lost a point there, right? So make it complete. Explain the 4-digit code. If I'm saying H5N1, what does that mean? Versus H7N9. Now, in this statement, I mean more than hemagglutinin and neuraminidase. There's something more to that. We want to see that. Explain how a virus can selectively infect a host organism. Describe the structure and function of hemagglutinin and the structure and function of neuraminidase. Now that's actually all you're being asked. And it's pretty search and find, but sometimes you look at it, see it, and miss the mark. So we want to make sure that we're really answering that. So we watched this cool clip about it, and you saw there are sialic acids on the outside of your cells. This isn't the virus. Where's the sialic acids on?
All of our
It's on
cells.
you. Yeah. Okay, so that's on your cells, and the hemagglutinin recognizes it, and the neuraminidase recognizes it. All right, statistical overview. Cold and flu. What are the odds of getting flu? Now I wanted to look this up for this year. This is last year's, okay? 5 to 20% of the US population will get the flu on average each year. 200,000 Americans will be hospitalized. 8,000 to 20,000 will be the people who die in the United States alone from the flu. Yes, most of them are elderly, but that's a real number. $10 billion spent on the average cost for the flu. 1 to 4 days before you're going to show some symptoms. And yeah, good times. Peak time, February. This is how many, the number of flu vaccines that are expected in the 2022-2023 year. And we'll expect it to be just about the same number, or a little bit higher this year. So, do you know what our number of the US population is?
300 million?
Yeah, about 350 million. So, you're looking a little over half of the population is going to get vaccinated, which means these numbers aren't talking about just because most people, you're talking about 1 out of 2. Are you getting it or are you not? Okay, now, that's a good start. Okay, let's see, what else? Oh, I want to click over here. Yeah, okay. Lots of good stuff. We're gonna look a couple other places. We'll come back to that. Anyways, let me get into some other stuff. We just looked at those. Let's see how many people died from COVID. Wasn't COVID as bad as they say? Well, this is deaths per 100,000. Wow. So over the United States alone, 1.1%
Of the population? Or of infected people?
observed cases. This is observed cases to fatality ratio.
Oh, so is that 1.1 person for every 100,000 died?
Yes, per 100,000 populations this one.
Okay.
So now you can look at it in more
Holy
comparable way.
cow.
So you come down and you say, okay,
Poor Peru, gosh, dang.
yeah, but is the US bragging?
No.
Did some other countries do a lot better than we did? It's your agency. We're too permissive in our culture to say, it's my right to wear a mask or not wear a mask. It's my right to get vaccinated or not vaccinated. Other countries don't do that. Could we have saved more lives? Yeah. That's not something that I'm saying is right or wrong. I appreciate agency. You appreciate agency. It's part of the plan. But sometimes you have to wonder, oh, little child, you don't seem to be understanding. You're going to die. And so what do we do to a child instead of let them run out in the street?
Rules.
We grab them. We make rules. We enforce things. Is that the right thing to do for an adult? Question. So there you go. There's your view of vaccinations in my estimation. Do I think they work? Yep. Why? Because the science is on my side. All the hogwash you can think that it's going to cause this or that of it, yeah, whatever. Bring me some data. And when you do, I'll go, really? Look at this versus this. You're scientists. Look at data, let it speak to you. Stop letting public opinion of those who do not know dictate how you live your life. Because if you're dead, you're dead. If you're in the hospital, you're in the hospital. If that's your child, that's your child. Is that nationalist views? You are the ones who can influence for the right. Because you can look at data and see it for what it is. Don't believe it's some government conspiracy. What does the government benefit by saying, well, all these people are getting sick, let's just let it go. If we can kill our population, it'll be better. That's way bad. Guys, that doesn't make somebody look like a winner when everybody's dying. We want heroes. Oh, we saved you guys.
It makes it so I can put those radio chips in.
Yeah. What happened here? 1918. It's called, for those who are in the back, Spanish flu. The variant on that is H1N1. Huh. No. The first time we saw H1N1 again
The 70s.
was in 2009. Why were we frightened to death?
Because of the Spanish flu.
Because this is the same variant strain that killed 20 to 100 million people, and the population was not as high. Did the Spanish swine flu in 2009, your lifetime, when most of you probably got vaccinated that year, did it kill many people?
No.
280,000 people worldwide is not minuscule. But compared to what we were just looking at for the COVID, hey, we did great. Okay? So, deaths per 100,000 per age group. Okay, so wow. Case fatality rates. What's going on that's allowing us to change the ratios? What did we discover?
Vaccinations.
Okay, so this one killed the middle age, yes, that was fun. But what did we discover? Influenza was identified as a virus here in 1931. The first flu vaccine, 1942. Oh. So we started to understand what we could do to vaccinate. That's really where you start seeing that. By the way, is there other ways around this? I can just show you this because it's fun. You remember that everybody got freaked out because COVID had been synthesized in some lab? Look
Yeah.
what we did. We took RSV and we took the flu and we put them together
Oh,
in the lab.
it's like a human baby.
And they are better than ever. Yep,
We should use that on more.
we did that last year. Good times.
Hey.
It's a lab, so don't worry, we got this one. It'll never escape. No, not here, right? We did that in the United States. Yes, we did that in the United States. Yeah. Yeah. Okay.
We have a question.
Trying to make the most
So-
disgusting diseases.
Another thing so you sort of get things about this. Okay. You know what the flu is, how it spreads, understanding it, right? Okay. Types of flu, okay, avian, canine, swine, pig, variants, right? Antigenetic characterization. This is the word that it says in the paper, meaning when I grab the paper, and I pull it up, and you should be looking at the paper with me, and I start looking, it says in the first paragraph underneath the abstract, first column, about halfway down, such antigenetic changes indicate the requirement for vaccine update. Antigenetic differences are also used to classify influenza type A viruses into this many hemagglutinin and this many neuraminidase. That number today, by the way, is listed at 18, and does it get updated?
Yeah.
Yes, it does. Well, what is an antigenetic test? That's really what we're talking about. What is the antigenetic test? It's an antibody test. Throw the virus, red blood cells, there's hemagglutinin, and we see what works against it. We're really seeing if the antibodies themselves will recognize that virus type. So I'm using antibodies to tell you that you're type 1 or type 2 or type 3. So I have a different pool of antibodies for each type. And whichever one sticks, that's the one that I call it that type. Currently we have 18. Why would we have 16 that moved to 18? Because we throw our antibodies at, yeah, go. Mutations occur, changes structure, and then I throw the antibody at it, and if none of the antibodies stick, it's no longer in one of those classifications. It must be something new, okay? And so, sometimes the antibodies stick really well, and sometimes they don't. Why would that matter? Because if they stick really well, our ability to make a good vaccine is
Higher.
much higher.
Yeah.
Yeah. Okay. And we're looking at both the neuraminidase and the hemagglutinin. Do we look deeper? Yes, we do, but that's largely how we classify them. Okay. So does everyone understand then what H and N is standing for? Yes, hemagglutinin, yes, neuraminidase, but it's their antigenetic characterization by using a antibody panel.
In that antibody panel, are we just like throwing every antibody we can synthesize at them, or
Nope,
how do we
the
decide?
ones for those class groups.
Okay.
So when you see it in your paper, right, what do you see? You see this sort of.
They have like two different phylogenetic groups per hemagglutinin or neuraminidase.
Yeah, so you see this grouping
Yeah.
right here? This is phylogenetic relationships, right?
Yeah.
So this is just saying, based on your structure, based on your sequence, we think you look like
One of these
you
guys.
used to be this guy and now you're mutating.
Okay.
And so that tree continues to grow. And you can see it's branched with two main divisions, but it keeps branching further and further apart. That's for hemagglutinin. Is there one for neuraminidase? Absolutely, same thing. Two different proteins in the viral code, okay? So your question, Connor, was
Well, because
why not throw everything we have at it?
Yeah.
We could, but we're trying to characterize what antibodies did you previously have of the flu that you saw that we classified by years, that then we can say, looking at this variation, this one, this swine flu, it's looking really bad, okay? And why? Because we knew nobody in that population had seen it. You don't have a resistance to that option, that strain option. So that helps us understand the severity of the threat by not saying, can I stick an antibody to it, but rather to say, it's this type and this type previously had this selectivity into getting into cells and killing people.
Okay.
Okay? And also looking at history and saying, yeah, we haven't seen that in a long time.
So in other words, these antibodies we identified throughout our history of studying the disease as present in people who survived, or
Right.
something
So
like
again,
that.
thinking about what we, okay. Thinking about what we did right here, if the very young didn't die, the babies,
Mhm.
and if the old didn't die, what would you guess the old had seen? Why didn't they die? Normally the old die from the flu. Why was it all the people that were your age and my age?
People who hadn't been exposed to that variant before.
Yeah, so we're gonna guess what? That the flu existed prior, right? And they'd seen a form of at least H, if not N, they'd seen something close to it. But everybody who was middle-aged, not so much. And the young just were able to beat it because they were young. But to take out your age population, which is what it took out, okay? You gotta understand, that's virulent, that's dangerous. And so that's why they were concerned here, okay? Have we seen other killers? Yes, we have. So we've classified those and we're watching for that. So why is it an advantage to get the flu vaccine every year? What am I building up?
Well, each year they do tests on what's the likely chance of which strain it's going to be, to where it allows your body to fight off a little bit of it, so it can generate a lot more of the antibodies to recognize it.
Okay, good. So I might be able to keep it at bay and then develop better antibodies for it. Yeah.
If you get a flu shot every year, you get the antibody strain from that year. You're building up a panel.
Ah, he thinks like I do. Meaning, I don't really want to get the flu every year so that I can have antibodies for that strain that I got that random year 4 years ago. And then I don't see it again for 4 years. But if I'm getting it every year, what am I getting antibodies for? I'm getting the options out there and I'm like, okay, I can hit a lot of these really well because I've got these antibodies I built up. Does it make us invincible? Absolutely not, but it's a better odds. Okay? Does that make sense? That's kind of the strategy.
Why wouldn't they just make a flu shot that had every
Possible variant?
possibility that we've seen?
Yeah, that's a
I mean,
great
it's a
question.
small amount of liquid.
Great question. Do you think we should try it? We could, right?
From my understanding was that your body can only handle so much of certain types and identify to it before you get overwhelmed by having so much variation of infection, right?
Yeah.
So if you had all of these different strains of
I'm not
gin,
gonna believe, essentially, I'm going to try to recognize something in common in all of them, but what I might be recognizing might not be helpful. In fact, more likely it might cause what? An autoimmune disease. So, yeah. Okay. Little history on the influenza. We feel smart. Little blob, 100 nanometers across. Did you know in the mass spec I can inject a whole viral capsid and get the mass of the whole thing intact?
Wow.
Alive or dead, doesn't matter. It's got a sheath lipid bilayer. Where does it come from? The host. So the first ones that get to you, they have whoever they were in. But after they've been in you and they infect your cells, they look like you. They've got all the sugar code that they can from you. They're trying to make themselves look like you. But they have unique pieces that are not there, okay? Some 500 molecules of hemagglutinin and some 100 of the neuraminidase on the surface, okay? All right. This is a picture from the text of what? Four
that's the-
identical subunits.
That's the neuraminidase, I think.
This is neuraminidase.
Yeah.
This one up here has 3 identical subunits that when cleaved at a specific arginine,
Yeah.
then the identical subunits actually become dimers within that, little peptides, and that actually causes it to then fuse
With our membrane.
with the membrane. So before it binds, because it recognizes the hemagglutinin and sialic acid to your galactose and says, hey, we're happy. Once it's bound, it's still got to get inside. But the rest of the role beyond the binding protein is a fusion protein. And we'll talk about that in our next unit, not this one. But you can see that when it unlocks, what's it pulling together? Our cell membrane and the virus membrane.
Mm-hmm.
This is the part that we'll talk about later. It's a phospholipid bilayer. What's the charge on the surface of your cell membrane? Is it charged?
It is.
It is. And if I put 2 of the same charges next to each other, they repel. Oh, that's great, because that means all my cells don't just fuse together. That makes brilliant sense. Then how do I get things in and out? You see them going in and out. There's fusion proteins. That is also a fusion protein. So if neuraminidase had the 4 that look like, what is this type of thing? What is that called? Those arrows in opposite directions.
Beta sheets.
Anti-parallel beta sheets, which in the circular shape look kind of like they're what? Barrel shapes. Propellers is how it's described in the text. And what's neuraminidase actually doing?
Isn't that how it gets out at the end?
It cuts. What's it cutting? It's an enzyme. It cuts the sialic acids off. It recognizes the specific bond between your galactose and sialic acid. It says, I'm going to cut right there. So if I didn't have that specific linkage, neuraminidase wouldn't recognize it. So wait, so if hemagglutinin mutates from the bird flu and can get into my cell, do I still have a problem getting out of my cell if it hasn't mutated also on the neuraminidase?
Yes.
Oh, yeah, I'd have a problem affecting other cells. I need to have two sets of mutations that would allow me to top species. Well, that's intriguing. How many subunits, by the way, on the hemagglutinin? We said that before, 3, 4 on the other. So, is it possible that actually just leaving the cell, if I could block that, that would be a problem?
Yeah.
These are drugs. What are they blocking?
Imidase.
No, just.
This is sialic acid and acetylneuromidic acid. Sialic acid, same thing. Okay. Okay. This is where it binds into what? Neuraminidase.
Yeah.
But there was a mutation, so we designed a drug that looked just like this. I got a glutamate. Let's make it look like this. But maybe we can make it so that it doesn't gain entry, because it's just a drug that's going to bind in the binding pocket of the neuraminidase. That'd be great. So then if that's the case, it can't cut its way out. Which means the hemagglutinin itself would reinfect the same cell. Over and over. There are some viruses in their life cycle that actually explode the cell, and that's how they leave, and it works. It doesn't work for the flu. They need to actually leave and exit and grab the membrane layer. But a minor mutation occurred. It moved a histidine 274 to a tyrosine 274. What did that do to the glutamate here?
Conformational shift and pulled it up.
And so the drug
No longer fits.
doesn't work anymore.
Okay.
So drug design, structure determines function. Yep. Wow. This is the fun stuff. This is where we go in and we try to redesign drugs, okay, to make them work. Okay. New drugs, by the way, replace that one. So zanamivir, or violet, this is the other mutation trying to handle our new shape. Redesign knowing that now it's tyrosine, the glutamate's been moved. Can we get the positioning just a little bit better? Okay. For those that are resistant to the one, maybe we can get them with the other. There's all these different types, yay, yay, yay. This is the last piece I'm gonna say, and then it's your time, the whole time. Great. I left you 10 minutes, sorry. If that's sialic acid or neuraminidase acid, this is something called an alpha 2,3, this is an alpha 2,6. This suggests that it's connected to what? It is galactose. In fact, it's N-acetyl galactose. But there's the galactose here that we're looking at. That's the glucose. Galactose 2, sialic acid. This is the sugar code it's recognizing. Sialic acid, galactose 2. This one's a alpha 2,6, this one's an alpha 2,3.
Okay.
Did that change the shape?
Yes, a lot.
Yes, it did. So by doing so, we can talk about it. It turns out that avian and equine, what are equine?
Horses.
Horses, yeah. They prefer to bind to an alpha 2,3 linkage. So the reason you're not getting the bird flu is because you have an alpha 2,6. Turns out there's another problem. The swine, what are swine? Pigs. They actually express on their cells both types, alpha 2,6 and alpha 2,3. It turns out that it's fairly common in China, but it happens all over the world, that they like pork, they also like chicken, and because of poverty and where they're at, they'll often sleep in the same place with their chickens and pigs all together. Then they send their chickens out to graze, eat some worms, peck around, and other birds fly by with a bird flu of some random variant. And what does that have the ability to do to their chickens? Their chickens can get sick. And if their chickens get sick, and then they house their chickens and their pigs together, what's gonna happen to the pigs?
They can get sick.
Great, but the pigs could get better, but if it's a really bad one, the pigs might die. But what if the pig's able to survive? It's giving the virus more time to try to mutate. If the virus now recognizes that I could reinfect these same cells that also have alpha 2/6 on them, then I can start to build mutations for what? At least one, the hemagglutinin, and potentially two, neuraminidase. Which one's likely to go first? Either, but neuraminidase, because it's already encountering the other neuraminidase. And saying, well, maybe, so these are just random mutations. So don't sleep with your pigs. That's how it could get to you too, by the way. So.
Go with pigs. Don't do it.
And there you go. So you got lots to learn. You've heard my passion statements about these, but what are you trying to answer? Yeah, seems reasonable. When I look at the details, I see a bold with hemagglutinin. If you go down about 3-4 sentences and you say everything above that, you're probably going to say the right things. If you go down about 1 sentence, you're probably not saying the right things yet. I skip over a couple pages, and what do I run across? Neuraminidase, big, bold. I think I go down all the way here to where I sound like a biochemist. Instead of just saying it's a mushroom with a long stalk, I start saying it's a 6-bladed propeller-like structure, which blades are formed of anti-parallel strands in a beta structure. Oh, that sounds like biochemistry now. That's what we're talking about, okay? When I go back to neuraminidase, to hemagglutinin, a trimer identical subunits, cleavage of the precursor at a specific arginine activates the fusion part. Cool. That sounds like a good answer. By the way, I meant to look up, I started but didn't get very far. To my knowledge, we still haven't identified the enzyme that does that cleavage. Would that be a good drug target?
Yes.
Because if we could stop that, you could still bind your cells before you get in. That'd be awesome. Yeah.
For the code for the hemagglutinin and neuraminidase, do you want us to use like the given 16 and 9 subunits, or do you want to use the current amount?
I don't care. What I'm having you do is describe what are we talking about.
Okay.
So it's less about the number, so you can use 16 or 18, and more about its purpose. Okay. Awesome. Talk about it some more. I'll be around if there's any other questions you're running into.
I feel like this one's way more straightforward.
If you don't say alpha, and all you say is 2, 3, wrong. If you don't say sialic acid and galactose, it's wrong. Meaning sialic acid alpha 2, 3 versus alpha 2, 6. Well, what do you link to?
It's gotta be the galactose.
I gotta have it be the galactose. No bullshit.